Hello, chemistry students. Today we are going to be talking about molar volume and ideal gases. And this is the last video in our gas laws chapter. We're going to revisit this diagram that I gave you last semester in lesson 16.1. So at that time, our focus was on mass, moles, and representative particles. And I told you to fill out the volume part of the diagram, but we did not do any calculations using it. And I said that we would revisit it when we're talking about gas laws. So today is the day that we are revisiting our conversion chart. We're going to take a closer look at the relationship between moles and the volume of gas at STP. And you'll remember from the last video that STP means standard temperature and pressure. You should have those values written down in your notes, but if you do not, I will give them to you one more time. So for the temperature, it's 0 degrees Celsius or 273.15 Kelvin. The pressure is equal to 101.3 kilopascals or 1 atmosphere. Okay, so Avogadro's hypothesis between the mole volume relationship states that equal volumes of gases at the same temperature and pressure contain equal numbers of particles. And it does not matter if the gas is made from the same substance or different substance. So the value you need to write down and remember for these calculations is 22.4 liters. So if you have 1 mole of gas at standard temperature and pressure, it should occupy 22.4 liters. Again, we have standard temperature and pressure listed here. So if you know the number of moles and want to find the volume at standard temperature and pressure, you just multiply the number of moles by 22.4 liters. If you know the volume at standard temperature and pressure and want to find the number of moles, you will divide that volume by 22.4 liters. So here's our practice problem. What is the volume of 3.70 moles of nitrogen gas at standard temperature and pressure? So we know it's at standard temperature and pressure, and we are trying to convert from moles to liters. So we're going to pull back out our railroad track method for this type of conversion. And we're going to write down what we know, which is 3.70 moles. Of nitrogen gas. That goes over 1. And for every 1 mole, there are 22.4 liters. So 1 is going to go on the bottom so that those units cancel. And then there will be 22.4 liters on the top. When you multiply these two values together, you get 82.88. Because moles cancel out, we're left with the unit of liters. This problem gives us 3 significant figures, so 1, 2, 3, and that 8 will round up the other one. Our final answer is 82.9 liters of nitrogen gas. Okay, so this is the last gas law that we're going to talk about, and it's called the ideal gas law. It describes the behavior of an ideal gas, which doesn't exist in the real world, but we still use this equation, and chemists use this equation all the time because it works really, really well for real gases. It's pretty close. The difference between the ideal gas law and the previous gas laws that you've learned is that it involves four variables instead of three, and you can use it to study a gas without putting the gas through a change. So it's just studying one gas and then nothing happens to the gas. Okay, so let's define these variables. You should recognize a few of them already. So the first one stands for pressure. Then we have V, which stands for volume. On the right-hand side, there's a new one for you, N, and that represents the number of moles. We're going to skip over R, and the last one we'll talk about right now is T, which stands for temperature. Okay, so R needs to be included in every calculation, and it is a gas constant, which is used to make the math work pretty much. So the value is equal to 8.31, and it's going to be involved in every single ideal gas law calculation you do. The units actually give you a lot of information here, so let's color them. So these values in the constant tell you which values you need to use for all of the variables. Okay, let's do a couple of practice problems. At 34 degrees Celsius, the pressure inside a nitrogen-filled tennis ball is 212 kilopascals. The volume is 0.148 liters. How many moles of nitrogen gas are in the tennis ball? Okay, so we're going to write out our ideal gas law. PV equals nRT. What are they asking us for? It says right here, how many moles? Okay, so they're asking for N. Let's list out what we do know. The pressure is equal to 212 kilopascals. Volume is 0.148 liters. We know that R is going to be the same every time. It's 8.31. And then it has that long set of units. Liters times kilopascals divided by Kelvin times mole. The temperature is 34 degrees Celsius, which needs to be converted into Kelvin. Okay, now let's plug everything into our equation. And I'm going to write this unit out stacked so you can kind of see it a little better. And then our temperature, this value by itself. So we actually have to divide by everything else on the right side of the equation. So it will look like this. And now it's important to check your units and make sure that you're going to end up in the unit you want to end up in. So we're going to cancel out everything except for N on the right-hand side. And then over here, we have liters, that does cancel, kilopascals, that does cancel, and then Kelvin cancels as well. So we're left with moles, but it looks kind of funny, doesn't it? So it looks like this: 1 over 1 over mole. So that is actually just equal to mole, which is the unit we want. So we can plug these numbers into our calculator at this point. We're going to multiply everything on the top and everything on the bottom, and then we're going to plug those numbers back into the calculator and find out what the answer is. So when you divide those two numbers, you get 0.0122927 moles. And we are allowed two significant figures. This one, so 1, 2, and this 2 will not affect the other one. So our final answer is 0.012 moles. This is going to be our last practice. What pressure will be exerted by 0.450 moles of a gas at 25 degrees Celsius if it is contained in a 0.650 liter vessel? So this is going to be an ideal gas equation. Now, what are they asking for? They want to know what pressure will be exerted. We're looking for P this time. Now we can list out what we know. Our volume is 0.650 liters. There are 0.450 moles. R is always the same. And the temperature is 25 degrees Celsius. Okay, now let's plug everything in. Okay, this time it's a little easier. We need P by itself, so we just need to divide both sides by the volume. We'll check that our units cancel properly. So everything cancels over here. And then liters go away, moles go away, Kelvin goes away, and we are left with kilopascals, which is our pressure unit. And now we're going to plug everything into the calculator. So this is equal to 1,715.2799 kilopascals. We are allowed two significant figures in this one. 1, 2. The 1 won't affect it. So our final answer, I'm going to write this in scientific notation because it would just make more sense that way. 1.7 times 10 to the third power kilopascals.